not necessarily gradient descent algorithms. Okay, so anyway, I could go on about that, but I won't here. So in that view, federated learning is just about trying to collect a lot of data from a lot of people, okay? And maybe give them some guarantees and all, but really you don't care about the people at all. You care about Google, who's trying to grab a lot of people's data and then use it for their own purposes. And you're trying to build bigger models. Where do you get the data from? Well, you just grab it out there. So that's federated learning. An alternative is to say, no, we're trying to build these collectives. It's all about the people. Okay, the central thing is just kind of there to manage the thing. So it's all about these agents and empowering them and trusting them and giving them, access to not just how their data is valued, and it's also then about supporting the overall collective effort, which will do things that no one individual could do or no central entity could do. Okay, so hopefully you agree there's some value in thinking this way. I think it's actually a far more interesting thing to think about. And so now you have all kinds of problems that come up. Here's four I'm going to kind of allude to in this talk, but there's just tons. There's the usual federated learning kind of things about compression and gradients and all that. But there's all kinds of other more economics ones. Like how do you manage information asymmetries? The information is spread all over the place, and one person knows more about something than someone else knows. But that doesn't mean they're necessarily the leader. They may be the follower. It's how do you manage it, and you don't want to just transfer the data to somebody. You want to you have competitive advantage to holding your data, so you want to respect that. Uncertainty, we don't talk enough about uncertainty in machine learning these days, to my view, and that's a whole separate talk I would give. But how do you manage it in these collectives? How do you deal with all the biases, and then how do you incentivize? So if you don't put the word incentivize in there, you're not really doing full economics. Praneeth and I have been working on this, and he'll talk more about incentives later. Okay, so let me just jump in and give you an example of incentives meets machine learning. So this is a work with Stephen, Michael, and Jake at Berkeley. And so let me just say a couple of words about the theory of incentives. There's a book with that title, written by a French person, Lafont. And so roughly speaking, let's just start with game theory. You all know what game theory is. Game theory is not really the engineering field. Game theory is more of a science field. It's trying to predict behavior by making a model, running the model, putting players in a game and seeing the outcomes, and say those outcomes correspond to what I see in reality. It's just like a physicist who writes down some equations, runs the equations, looks at reality, says, oh, it's a good model because it matches reality. That's what game theory is doing. Okay? And now there's different kinds of games. There's symmetric games, there's asymmetric games, there's collaborative, and they try to explain different things in the real world. Okay? Now, an engineering mindset takes that in physics, and they say, we're going to do something called mechanical engineering, which is to invert the equations. We want a desired outcome, the bridge stands up. What are the principles that will give us that? In game theory, the inverse problem is called mechanism design. And there's for each kind of different game, there's a different kind of mechanism that arises. Most of the work you will read about in game theory and mechanism design is about auctions and about symmetric games. So if the game is symmetric, meaning all the players, there's no real distinction of a leader or a follower, they all come in. They may not know things about each other, so they have to average and all. Those are called Nash equilibria. The game concept is a Nash equilibrium. It's all symmetric, right? The corresponding mechanism for a Nash equilibrium is an auction. And then there's all kinds of different auctions, right? But auctions are about players who are symmetric. I think in our world, it's much more common to have asymmetries. Okay, you come in and someone knows more about something than someone else, and everyone recognizes that. That's an asymmetry. All right, so in the game theory world, asymmetries are called Stackelberg games, and you have Stackelberg equilibria, and there's a whole field there. But now what's the mechanism that is the inverse of a Stackelberg equilibrium? That's called contract theory. Okay, so hopefully that helps place everybody. So if you want to work on mechanism design with asymmetries, that's exactly contract theory. So you all know a little bit about what contract theory is. It's that you have these agents, and a principal wants to get them to do something or to buy something or whatever, but they know things the principal doesn't know. They have some skill, and so the principal would like to get them to use that skill in some way. Or the principal wants to get them to buy something. So airplanes are the best example of this. It saved the airplane industry to start using contract theory in the 1980s. And what does that mean? Well, they invented the whole notion of different classes of service. So business class gives you a little bit more of a service, and you pay a lot more money. But there are people whose price point is such that they will go ahead and pay that, and then the airline reaps the benefit, and then there's a few seats filled at a high fare, and then lots of other seats are available for lower fares where people don't have the same price point. So the overall social utility is high. Everybody gets something they kind of want, and the airplane is full, so the revenue is high. And if you design it right, it kind of works over many years, and you tweak it and all that. And people, of course, hate the airlines because they do this. But in some sense, there would not be airlines if they didn't do this. Okay? All right, now this isn't, there's lots of other domains where you're trying to get like a boss wants to make a worker do something, and the worker knows something about their skill, so they're trying to get paid a certain amount, and there's this asymmetry. Okay. So anyway, the theory is really quite vast, but what's interesting, there's almost no statistics in it. There's no statistics, there's no learning. These agents aren't learning anything. Some designer, like the airplane, sat down and designed some things with some crossing curves and some equilibria concepts. All right, but then you put it out in the real world and hope it works. If it doesn't work, you tweak it a little bit. So that's a huge opportunity for people like us. How do we think about asymmetry of information and learning systems? All right, so here's a real-world concrete example that has driven some of our thinking in this. You all know what clinical trials are. They cost tens of millions of dollars each year to run. It's an asymmetry of information situation. It's not thought of that way. The FDA in the United States thinks of themselves as a statistician. They're testing hypotheses, and they're trying to make sure false positives and false negatives are managed. Okay? The problem is that the hypotheses aren't just coming out of a scientific theory or just out of the air or something. They're coming from self-interested agents, the pharmaceutical companies. All right? So you're not just testing random hypotheses. All right, so these numbers reflect partially that uncertainty. So let's dig in a little bit more. The principle is the FDA. So this language is, you say in Statistical games, you say follower and leader and follower. And when you do the inverse thing and you do contract theory, you call it principle and agent. That's just language. All right, so the principle is the FDA. They only have partial knowledge because here's a new drug candidate. It's some protein that's been altered in some way. And the FDA doesn't know anything about that protein, really. But the pharmaceutical company knows a lot about that protein. They've been studying it for years. They've tried it out and all that. And plus, they've done maybe some internal testing and so on. The FDA would just like to ask this agent, tell me how good your protein is. The agent is not motivated to tell for competitive reasons, and also they want to get good licensing terms and so on and so forth. So they won't. They will lie. Okay? And this happens all the time. People lie for all kinds of good reasons. It's part of how humans are. Okay, so how does the FDA actually think about this problem? Well, I will argue they don't think about it the right way. They think about it too much like a statistician or a machine learner. So they think, okay, the world has, let's suppose, good drugs and bad drugs. Bad drug doesn't mean it hurts anybody. They screen for that. But bad drug means it's just not effective, doesn't do anything. Good drug means it really changes things. It makes things better. All right, and they set it up so that if it is a bad drug, the probability of approval is like 0.05 or less. That's the false positive rate. And if it's actually a good drug, the probability of approval is 0.8. That's the power. And they're really good at this. They're really good at the statistics. Is this a good protocol? Well, it's optimal. It's the Neyman-Pearson test. You can't beat it. All right, but it's not a good protocol from a game theoretic point of view. So in case one, let's imagine small profit to be made. So 20 million to run the trial, that's the numbers you saw. And if you're approved, maybe you make 200 million. It's a small niche drug. Okay, so the CEO looks at that numbers, all these numbers, and does a little calculation. The expected value of the profit, if counterfactually the drug is actually not effective. No one knows that. The CEO doesn't know that, the FDA doesn't know. But if counterfactually, let's just imagine for a moment, do the thought experiment, it's not effective, then I will on average make minus $10 million. All right, so the CEO looks at that number and she says, okay, engineers inside my company, only send in drugs that are really, you're pretty convinced are effective. Otherwise, we're going to be losing money. So in that moment, the incentives are aligned and the FDA gets mostly good candidates. And when they do their Neyman-Pearson testing, good candidates go on the market, everything is happy. The real world is more like this thing on the right. It costs $20 million to run the trial. And if you're approved, you might make $2 billion for the first year. That's more like ibuprofen or lots of more other drugs. And now the CEO does the same calculation. She finds the expected profit, if my drug counterfactually were not effective, is going to be 80 million. And so now she goes back to the engineers inside the company and says, send in everything you've got. Okay? Flood the FDA with all the possible candidates. So why are they doing that? Well, because of that 0.05. And it's actually like 0.001. But anyway, that number is big enough that if you send lots and lots of candidates, some of them will squeak through as false positives. They will go on the market, and your expected profit is huge. And so you do that. And people, these drug companies absolutely do this. So lots of drugs on the market are, in fact, if you retest them later, they're not effective because of this. Now, is that bad? Yeah, that kills lots of people because people could have had a better alternative and they were taking something that wasn't actually helping them. So the market eventually corrects and so on. The FDA starts to get a reputation and so on, but this is not good. All right, so how do you fix this? So long story short, we've developed a theory. We call it statistical contract theory. It's just getting going. This is brand new. And just roughly, here's a contract. So what is a contract? It's like the business class. In general, a contract is an option and a price. Option, price, okay? Business class, economy class. So here, the options will be things like different licensing terms you might have, okay? Where you can do it, how much you can do it, how long, and so on. And then, the price to enter into the clinical trial. Okay, so agent will be given this option, this protocol, and the agent can either opt out and say, forget it, I walk away, I'm not gonna try it with this particular candidate, or they can say, okay, I'm in, I pay a reservation price R, like 20 million, then they're gonna choose a payout function from a menu, and here's where the machine learning comes in. What payout functions do we use? Well, we're going to design that, okay? We're gonna choose those. And that's going to be where all the interest is. And now the new component here is that in classical contract theory, there was no data gathering. Here there's data gathering. You gather a random variable z, which is the clinical trial, which is drawn from the true distribution out in nature. No one knows theta, but nature does. So you draw from nature. All right, and now you get the payouts. Agent receives a payout, which is F, the thing they chose, applied to that. And the FDA gets a utility. They have to, pay out that amount. So they pay that, and then theta as well. It depends, because they will get reputation if they approve good drugs mostly. So our problem as designers is to design this menu. So what kind of menus are reasonable? Well, first of all, you have to write down a notion of incentive alignment. If you don't write that down, you're not doing economics or mechanism design. And so here it's pretty interesting and straightforward. The incentive alignment is the expectation under the null hypothesis, right, of how much it'll cost you minus the reservation price, okay? So you want that to be negative. This is the agent's expected profit. If that were positive, the agent would have expected profit, which is positive. That would not be good. So we got to make sure that this holds, and it really is only under the null hypothesis that it matters. All right, and so now we can prove a theorem. And it's right here at the bottom of the page. We can prove that a contract is incentive aligned if and only if, it's the only if which is key here, all payoff functions are E values. So I'm up to 50, oh, you're going in the opposite direction. Oh, usually it's a count down. Okay, all right. All right, so yeah, fine, I'm gonna finish up here pretty quickly. Okay, so what is an E value? Well, E value is a measure of evidence in statistics. Okay, you all know what P values are. They're kind of bad measures of evidence from last generation. E-values are better. An E-value is an expectation under the null hypothesis of a non-negative random variable being less than or equal to 1. If X satisfies that, it's called an E-value. More generally, these are non-negative super martingales. And so you should think about it like a p-value is the probability on the null hypothesis being on the tail. If that's a small number, that's evidence against the null hypothesis. Okay? Here, under the null hypothesis, it's an expectation, not a tail probability, that's less than or equal to 1. Okay? So if it's less than or equal to 1, that's kind of evidence, it's not evidence against the null hypothesis. But if it's a big number, that's evidence against the null. All right, so it's just a different way of kind of thinking about null hypothesis testing, but it's much better because martingales, you can have stopping theorems, p-values don't. You can put martingales together, p-values you can't, and so on. Anyway, that's the statistics side, but what we've shown here is if and only if. That if you're going to design statistical contracts, you should only use the world of non-negative super martingales. All right, so that now tells you as a machine learning person, this is the objects we have to learn and we work with in our learning protocol. Okay? Okay, so long story short, we've been doing that in several follow-up papers. Since I only have 15 minutes, I'm going to stop here and not tell you about those follow-up papers. But we have some papers where you incentivize in the federated learning setting agents to provide data. You ask agents to provide more data. It has a cost. Statistical contract theory will apply there. And again, I think a couple of the other people in the audience will follow up a little bit on that. That's all I want to say. So I had a second part of the talk. Let me skip that. Let me just advertise this one. I'm not going to get into it. But this is a paper that appeared in Science 2 weeks ago, and we're pretty proud of it. It's also about uncertainty and different, two agents. But here, one of the agents is AlphaFold, okay? And AlphaFold provides biased data, and the other agent is someone who wants to use AlphaFold to do science, okay? AlphaFold generates lots and lots of data, but some of it's bad for especially the scientific hypotheses you're interested in. Okay, so let me just show you an example real quick before I go. Here's some pictures of AlphaFold. Here's the scientist in the lab, and here's AlphaFold. AlphaFold can do hundreds of millions of sequences. Scientists can only, up to date, only have hundreds of thousands. So if you start using AlphaFold to do hypothesis testing, here's an example of a hypothesis test. You can go from 10,000 data points to huge numbers. And let me show you a picture that'll convey the issue. Right, so here is an AlphaFold prediction, and here's the actual truth. AlphaFold's quite bad here, but it's good overall. The accuracy is overall high, but it's bad here. Why? Well, this is a situation of these strands of intrinsic disorder that AlphaFold doesn't have a lot of training data on, but this is exactly what the scientists are interested in. This is on the edge of knowledge, and that's often going to be the case. If you want to be on the edge of knowledge, there's not a lot of past data, and AlphaFold will make a lot of errors there, and so it's going to hurt you doing science, okay? And so now if you plug all the AlphaFold stuff into a hypothesis test for this particular thing, does intrinsic disorder have anything to do with protein viability, activity? Here's what happens. And so this slide I want to just spend 1 minute on, then I'll finish. This is a statistic here. It's an odds ratio. If the statistic is 1, there's no effect. If it's bigger than 1, there's an effect. So big deal, all right? If you use AlphaFold's output, here is the confidence interval you get. Small confidence interval. You have a huge amount of data from AlphaFold. So you get really high confidence, right? But we did a big Monte Carlo experiment on half of the AlphaFold output, and here's the actual truth. Yeah, this is not covering the truth at all. So it's wildly off. Even though the overall system is accurate, when you use it for hypothesis testing, it can be wildly off. If you say, forget AlphaFold, let's just use the ground truth data, you get this confidence interval. It's a classical statistical confidence interval. Unfortunately, it covers 1, and you can't make any conclusions. So we have this new approach called prediction-powered inference, which gets the best of both worlds. It's going to use the AlphaFold stuff, but it's going to correct the biases and allow you to do unbiased hypothesis testing. And we've done this in a whole bunch of domains, in computer vision problems, and other biological problems, in voting problems, and so on and so forth. And so I'm going to stop, but I'm not going to tell you how we do it. But if you want to come up to me, I'll tell you how we do it. It's sort of a new statistical idea. It's not completely new, but it's a new statistical hypothesis testing idea. Okay, so anyway, that part of the talk I didn't give much detail, but again, it's about an asymmetry. It's about some knowledge or some object over there that someone designed, which has some purportedly some knowledge, and there's you wanted to use that, and there's this asymmetry. How do you manage that? That's my big issue. All right, thank you.
Any quick questions while Samuel sets up? So maybe I can ask a question. How do you think these ideas would work if the knowledge needed to make a decision is sort of distributed? So in the talk, you were the agent was the manufacturer, the pharmacy company. There was just one company which knew all the right information. What if this information is distributed across multiple people?
I mean, the contract theory is about distributed asymmetries, right? So I think it arose, there was general equilibrium theory, which just is about producers and suppliers and finding a price, and then now the quantities that everyone should go for. But now if you go inside of an actual company, you've got managers and you've got workers, and the manager says, oh, the economic theorist told us our target should be X. How do you actually execute? You can't just tell people to produce X. You have to incentivize them. So it was about that. So there were multiple managers and there's multiple agents, and there can be asymmetries in both directions. I'm particularly interested right now in a problem where you have a hierarchy. So I'm a principal to some agent, trying to get Alan to do something, but I'm also a agent to some principal. Eric is trying to get me to do something, all right? And how do I behave when I'm both a principal and an agent? That starts to get into really interesting architectural questions, and those are not been asked in classical contract theory. There's lots and lots of things. It's not hard to think of them where you get into all these asymmetries. And I don't think contract theory answered, but a small sliver of them, because they were focused on a certain set of problems, save the airlines. But just this mindset to me has been very, very helpful in kind of liberating me from classical machine learning thinking.
Thanks so much, Matt.